As promised, we now need to take a look to see if we've actually done any better with these iterative techniques over the least squares techniques. So let me remind you where we were. Least squares, quadratic error function, E of u is equal to vector norm xu minus y squared. Here's the least squares solution. X transpose x, matrix multiplication, inverse, expensive, x transpose y. Remember that matrix multiplication and inverses are O of n cubed. You can actually do a little bit better with some optimization. You can get to about 2.7 or so, but it's expensive. So we introduced this notion of an iterative solution, either moving perpendicular down that quadratic error surface or moving a little bit smarter so that you'll have to take a fewer number of steps, fewer iterations, less costly. Let's just talk about steepest descent right now. So how did we get to steepest descent? We took that quadratic error function, we wrote it out with the quadratic form here, and then we had this update rule. U1 is equal to U0 plus alpha times the direction of steepest descent. What was A? A was, x transpose x. What was B? Well, B is cheap. It's just the matrix times the vector, so I'm not going to worry about that. So have we done any better? Well, I don't have to invert the matrix. That's good news because matrix inverse is also O of n cubed. So if that matrix is now with only 2 parameters, it's 2 by 2. So I don't care about that. But as you get more and more parameters, hundreds, thousands of parameters, which is certainly not out of the question for a linear model, that matrix is going to be, inverse is going to be expensive. We get a savings here on the steepest descent because I don't have to invert the matrix, but I still have to compute x transpose x. Now, I only have to do it once. This is the same A matrix on absolutely every single iteration, but I also only have to compute it once over here. So we got a little savings, but we haven't really saved where I really wanted to, which is on that big matrix multiplication when I have a ton of data points. And that's a little disappointing. And so it's going to turn out that what we're going to do is instead of doing the strict steepest descent, we're going to cheat a little bit in order to really save on this matrix multiplication. And that's going to get us to the third iterative solution called the gradient descent. And sometimes, by the way, people interchange these terms and we have to be very careful. Steepest descent is a very specific optimization where you move perpendicular fixed lengths until you get to the minimum. Conjugate descent is where you move exactly 2 steps with n steps with n unknowns to get to the minimum. And gradient descent is the idea that you're going to move downhill, but I don't want to go to the expense of computing the direction and the step size because that's still expensive. And so I'm going to cheat a little bit and hopefully still make my way to the minimum. And here's what that looks like. Same stuff as before. We're going to generate some data. We're going to pack it into the matrix X. But now notice I'm not building the A and the B matrix in vector. And what I'm going to do here is that I'm going to pick the direction as before. And notice, by the way, that there's an x transpose here, but notice I'm going to multiply x times u minus y. That gives me a vector here. And then I'm going to multiply that vector times that matrix. So I'm not actually multiplying x transpose times x to compute this gradient direction. And now what I'm going to do is there's my a sub I, my alpha. What is that? I'm going to fix the step size. And the reason I'm going to fix the step size is because that's expensive to calculate. That's what required that expensive computation in order to determine it. And I'm going to fix it to be 0.1. Why 0.1? We'll talk about that in a second. And then everything's exactly the same. I've got a direction which is cheap to calculate because I'm not multiplying those matrices. I've got the same update rule. By the way, the minus sign is here because I just didn't put the minus sign up here in terms of the direction. And I go over and over and over again until I get to a minimum, which is defined to be this. Now, if I can go back one slide, notice that there's lots of steps here. Why? Because look at how small I'm moving. I'm not taking a big step until I get to a minimum and then a step and a step, but I'm just very slowly going down the hill, making sure I don't fall. And the reason I'm doing that is for computational efficiency. So I've paid a price here in terms of iteration, but the cost of each iteration is much, much less. Now, there's obviously a price to be paid here, and the price is how do I know what the step size is? And in fact, if I pick the wrong step size, I'm in for a world of hurt because I start at some point and I step too much, I overshoot. and then I overshoot again, and I overshoot, and you create these instabilities, and you never, ever get to the end. So there's a little black magic involved with this very efficient gradient descent, but if you have big runtime efficiency problems because your data set is enormous or because the number of unknowns is enormous, you're going to have to sacrifice something, and you're going to have to tune that parameter until you get stable optimizations. All right, that brings us to the end, and so let me summarize. We started off with least squares and, of course, weighted least squares and total least squares. Those were the closed form analytic solutions for minimizing quadratic error functions that are of models that are linear in the unknowns. We were a little bit worried that when those matrices got big, it was going to be costly. And so we derived steepest descent and conjugate gradient descent, which seemed to be a more efficient in terms of number of iterations. But this saved us something, but not necessarily everything we wanted. But they led us to it. And this could seem like, well, what was the point of all of this? Why, for the love of God, would you introduce and make me go through all that math to get to steepest descent and conjugate gradient descent, only to say there's this hack here where you're going to pick the step size? And of course, the reason is I wouldn't have known what the hack was until I've actually derived this, figured out what the complexity was, and then how do I approximate that? So think of gradient descent as an approximation to these nicer closed iterative solutions that are going to guarantee us to get to the minimum. So there was still value in here because now we see why we're doing what we're doing and where the approximation is. Now there's one more thing I should mention because you'll hear this particularly in machine learning called stochastic gradient descent. So another way to get savings here is don't use all the data. If I've got a huge data matrix and I'm trying to fit a linear model, maybe I can throw away some data. Maybe on each iteration, I can use a different subset in order to do the estimate so that I can be more efficient. And we won't talk too much about that right now, but eventually when you take your machine learning course or your advanced computer vision course, you'll hear more about stochastic gradient descent. It is essentially another trick in order to make steepest descent and conjugate gradient descent more efficient. All right. All of this, least squares, weighted least squares, total least squares, and all three of these iterative least squares are supervised learning regression techniques. It's easy to get bogged down in these details and all of the algebra and linear algebra, but remember what we were trying to do here. We are trying to estimate a real valued function that takes as input something and hands me back a real value, not categorical, not face, not face, object A, object B, object C, but a real valued. I'm trying to predict a number, and that is the so-called supervised learning regression. And least squares and total least squares and these iterative least squares are the workhorses of these techniques. Many other techniques, interesting, very applicable. Many of them build on these as the building blocks. So it's incredibly important, not just for practical purpose, because you will absolutely implement these techniques, but these also form the building blocks for which future techniques you will learn about either in this class or in subsequent classes.